Hello, welcome. This is the video lecture on bolted joint analysis and design. Earlier in class, we talked about thread systems, threaded fastener types. We went through in some detail power screws, and there's a video on that as well. In this video, we're going to talk about design and analysis of bolted joints. We're going to discuss design for manufacture, installation of bolted joints, bolt strength and stress concentrations, bolted joint forces and compliance, external loads, preload and torque specifications. We're going to learn how to design bolted joints with respect to yield failure, rupture failure, separation failure, and fatigue. Then we'll conclude with one possible process for going about bolted joint design. Let's talk about design with threaded fasteners. First, design for manufacture. There's a concept called concurrent engineering where we need to look at design decisions regarding both system performance and how we're going to manufacture the system simultaneously. Boothroyd and Dewhurst have both a textbook and software that helps with design for manufacture. Here's an image of the textbook. Here's a screenshot of the software. This software helps engineers to determine how design decisions impact both cost and manufacturability. Let's talk about the impact of using threaded fasteners on manufacturability. Threaded fasteners do have associated with them a higher cost than other options and some increased manufacturing and assembly difficulty. The parts are sometimes more costly. It requires machining and additional skilled assembly time. So are there fastening alternatives with lower cost, reduced complexity manufacturing? Yes, adhesives is one, snap fit assemblies, and also welding. There are other options besides these as well. Another relatively new manufacturing process is additive manufacturing, where sometimes assemblies can be manufactured all at once, eliminating the assembly step. Here's an interesting example shown on the right. This is a dress made of rigid links that are connected together using revolute joints. Here's a close-up view of some of these revolute joints and the links. And the unique thing about this type of product is that can be printed in a folded up manner inside a small 3D printer volume. And then it's all assembled. It can be unfolded from the small 3D printer volume. So in other words, this dress can be folded up small into a compact volume, and here's an animation showing the folding. So it's possible to print a large product in a small volume. So if there are all these options beyond threaded fasteners, why would we consider using them? There are lower cost, easier to assemble alternatives. One of the main reasons is if we're interested in non-destructive disassembly. This makes it easier to repair systems, especially if repair needs to be done away from a manufacturing facility. Using threaded fasteners could also help reduce life cycle cost if it enables easy maintenance. Here's an example of one system that uses threaded fasteners. At the bottom left is an automotive engine block, and up toward the right is the cylinder head. And this is a very critical connection between components in an engine. And here we can see the bolts that are used to secure the cylinder head to the engine block. Here's another example with a bolted pipe flange, and another from your textbook, a pressure vessel cap with a gasket. Let's talk about the function of bolted joints. So threaded fasteners clamp two or more members together. Well-designed bolted joints can resist a variety of load types, including external axial loads, shear loads, moments, and other types of loads. When assembled, tension in the bolt shank produces a clamping force on the joint members, even if there's an external load, as shown in this figure. Let's talk about assembly and maintenance. It is very possible to install bolted joints incorrectly. And if this is done, it can reduce strength or cause other problems. And this is especially important for safety critical applications that installation is only done by individuals who are trained. So when assembling a bolted joint, it's important to use high-strength washers to protect the bolt head and the nut from damage. When we drill a hole through the members for a bolted joint, it sometimes can leave sharp edges, and these could damage the bolt head or the nut if we did not use washers. When installing washers, it's important to notice there are two sides to them. There's a rounded side, and then the other side is a little bit flatter and sharper. It's important to install the rounded side facing toward the bolt head, as shown at the top of this figure, or the rounded side facing toward the nut at the bottom of the figure. We want to make sure that the rounded side is not contacting the member. When installing a bolt, it is preferred to hold the head of the bolt fixed and then rotate the nut. This is not always possible, but that's the preferred strategy. As we tighten the nut, that's what creates the tension in the bolt. It's good to design bolted joints and size the bolts such that you have about 1 or 2 threads protruding from the end of the nut after tightening. Let's talk a little bit about manufacturing. There are standards for bolt hole clearances depending on the size of the bolt. You can look those up in manuals such as Machinery's Handbook. Threads need to be cut into members when we're using cap screws. So the process of cutting these threads is called tapping. And on the left, we can see a tap that is being twisted into a hole to cut threads out of the hole. Sometimes, if during use threads are damaged, maybe during maintenance or repair, it's possible to restore these threads by using a tap to recut the threads. Or another option, if the threads cannot be restored using tapping, is to install a wire thread insert. And the basic process is to drill out the hole larger than it was originally, and then cut larger tapped threads into which we install a helical wire thread insert. Let's talk about thread yield. So if we have a bolt shank in tension and we're pushing back on the nut that's threaded onto this bolt, when the nut is first tightened, this first thread, that takes pretty much all of the load. But after the initial tightening, due to plastic deformation, due to yield, the threads adjust so that the load is spread out a little bit more evenly. And the nuts are designed this way. They're designed to yield. And after the plastic deformation, the load is spread out over the first 3 threads. You might remember this is very similar to what we talked about regarding power screws and the load distribution and the strength of power screws. It's important to note that because of this deformation, we really should not use a nut again after it's been tightened and used in the bolted joint. Sometimes we can reuse bolts, but we should not reuse the nuts. This type of system is a statically indeterminate structure, similar to what we looked at with power screw threads. And we'll have a look at this in a little bit more detail later in this video and learn how to analyze the forces involved in bolted joints. So after tightening and yield, the tension relaxes, and it's important to retorque the bolts after this happens. For example, the automotive engine cylinder head that we saw, usually the specifications the manufacturer provides for installation of a cylinder head along with a gasket specifies the order in which the bolts are to be tightened, usually in stages, and then after the final tightening and after some time has elapsed, then you go back and tighten everything again. And I've mentioned earlier as well that nuts should not be reused as they are designed to yield after tightening. Let's talk about what are the major failure modes for bolted joints. One is rupture. If we go to an appropriate table, here's one from your textbook, we can look up the strength of different bolts. And so this can occur if we have a load applied to a bolt that exceeds the tensile stress area, A sub T, times the ultimate tensile strength of the bolt. This strength depends on the grade and material of the bolt. The proof load is lower than the tensile strength of the bolt. This is the maximum load that we can have applied to the bolt without incurring a permanent set. The proof load is equal to the tensile strength area times the proof strength of the bolt. Fatigue is another possible failure mode, considering especially that bolts are in tension. There are a few locations where crack initiation is more likely, including the head fillet, the first thread root, and then the first nut thread that takes the majority of the load. Another possible type of failure is separation, where we lose clamping force between members. Okay, now we're going to go through a section where we learn how to predict the forces in bolted joints. As I mentioned before, these are statically indeterminate structures, so we need both the equations of static equilibrium and elastic deformation to predict forces. Let's have a look at this simplified example. Here we have two rigid bodies on the top and bottom. They're held by rollers, so they're constrained only to move vertically. And we have two structural rods connecting these two rigid members, rod 1 and rod 2. These are constrained to elongate only vertically, and suppose we're applying a force F, and these bars are then in tension. But because we have two bars instead of just one, this is an over-constrained or statically indeterminate structure. So if we apply a particular load F, we might ask, how is this load distributed across rods 1 and 2? Well, here's the static equilibrium equation from Newton's second law. The total force F is equal to F1 and F2, the axial loads in each of the rods. Well, we can't resolve what these loads are in the individual rods through static equilibrium alone, but we can apply elasticity. So if delta 1 is the elongation of rod 1 and delta 2 is the elongation of rod 2, we can observe that with the rigid bodies on top and bottom, the elongation of each of these rods is constrained to be equal. And so that's what this equation is doing. We're saying delta 1 is equal to delta 2. And just thinking back to basic elasticity, the stiffness of a rod, K, is equal to AE over L. And we can use that in these elasticity equations. So this gives us two equations and two unknowns, the unknowns being the force, the axial force in each of the rods. Given the elasticity equations, we can see that a number of things cancel, and we can say that F1 is equal to A1 over A2 times F2. And then if we rearrange the equation from static equilibrium, we can say that F2 is equal to F minus F1. Now, if we do some substitution, we can get everything in terms of F1, and then we solve for F1. And if we know what F1 is, we can plug that into the equation for F2. F2 equals F minus F1. Suppose P is an external load applied to the members of the joint. Here we are assuming it is applied such that the bolt will be in tension. P sub B is the load experienced by the bolt, and P sub M is the load experienced by the member. The bolt and the member, as in the previous example, are constrained to have the same deflection. So we say that the load divided by the stiffness for both the bolt and the member is equal to the same deflection. And then we also have an equation from static equilibrium. The load is equal to the bolt load plus the member load. One convenient way of quantifying these items is to look at the portion of the external load that is carried by the bolt, and that's P sub B. We can express P sub B in terms of the bolt stiffness and the member stiffness. And this quantity, K sub B over KB plus Km, that is a stiffness coefficient, C. And we'll see this used several times later on in this video. This value C tells us what proportion of the total load is taken by the bolt. The external load carried by the member, P sub M, that's equal to the total load P minus the portion of the load carried by the bolt. The actual axial tension in the bolt has two components to it. This is F sub B, and we have the portion of the external load carried by the bolt. But remember, when we assemble a joint before we ever apply any external load, we tighten the nut, and that produces some tension. We call this preload. F sub I is the preload of the bolt. And so that adds to the axial tension of the bolt in addition to the external load. Now, with these equations, we had a number of stiffness values that we needed to calculate. We needed to know what was the stiffness of the bolt and what was the overall stiffness of the members. In this section, we're going to learn how to calculate both of these values. Bolts often have two different sections with two different stiffness values. There's a shoulder without threads, and then there's a threaded section. The grip is the length of the member that's being compressed by the bolt. A rod stiffness is equal to the cross-sectional area times Young's modulus divided by the length of the rod. We can apply this to the two different sections of the bolt and obtain the stiffness of the unthreaded section and the stiffness of the threaded section. So which stiffness coefficient is larger? For equal length sections, K sub D, the stiffness of the unthreaded section, is larger. It has more material. Now, how are we going to combine the stiffness of these two different sections? We can think of this as two springs in series. They're stacked on top of each other. And so whether we're compressing or extending the springs, we need to learn how do we take K1 and K2 and combine them together to get the overall stiffness. This is different from springs in parallel that are shown on the right. So to calculate the stiffness of springs in series, we use this formula. It's very similar to calculating the capacitance of capacitors in series. And then in parallel, if we have two springs in parallel, they strengthen the overall stiffness. We're going to just simply sum the stiffness of springs in parallel. We want to know the overall stiffness across the grip length. And if we use the previous formula, along with the stiffness of a structural rod, we can derive this formula for K sub B, the stiffness of the overall bolt across the grip length. So here, A sub D, that's the unthreaded section area. L sub D, that's the unthreaded length. A sub T, that's the threaded section area. L sub T is the threaded length. And here, because it's the same material in both sections, E is the modulus of elasticity. So why would we include a shoulder on a bolt? Why not just thread the entire bolt? This can help increase axial stiffness, and for joints that are loaded in shear, it can increase the shear strength of a bolt. Okay, now that we've looked at bolt stiffness, let's have a look at member stiffness. Members can have two or more clamped members. We can think of these as springs in series as well. So we've seen a formula for how to analyze springs in series, but only for two springs. So what if we have a larger number of springs? Another complication is that we may have different materials in this bolted joint, and each member in the bolted joint may have different thicknesses. So if we want to add more than one spring in series, we use this formula. But getting the individual stiffness values for each of the members can be difficult to determine. There are some simplified approximations that are available in some cases, but in other cases where the geometry is more difficult, or if we want higher accuracy, then we may need to use something like finite element analysis to estimate what these stiffness values are. And of course, we can use experimental testing. There is an empirical model that is fairly easy to use, given in the textbook, that can help to estimate what member stiffnesses are, and it's based on experimental data. One big limitation is it is assuming we're using the same type of material throughout the joint. Here, D is the major bolt diameter, and A and B are constants that are material dependent, and you can look those up in a table from your textbook. Now, let's look at a model that we can use to estimate member stiffness, and we'd like to use an approach that's easier than using finite element analysis. The strategy here is to approximate the geometry of the pressure cone, or the region in the member that is experiencing deformation from the clamping force of the bolt. And the geometry that we're using in the simplification is a truncated cone, or a frustum. So the frustum model given in your textbook is shown here, and the quantities in this formula are shown in the diagram up above. It's derived in the textbook. It's more general than the exponential curve fit that we just looked at. It can accommodate different materials. The way you do that is you calculate K for each of the members in a joint, and then you add those K values in series. Keep in mind this is still an approximation. Finite element analysis or experimental results will be more accurate. Here's a comparison of a number of different member stiffness modeling strategies, and these are all compared to the results from finite element analysis. So here's the curve corresponding to the finite element analysis results, and here's the most accurate model. And these models, one of the assumptions is, well, what is the angle of the frustum in the pressure cone? And it turns out using alpha equals 30 degrees results in a pretty accurate model. Another type of joint to be aware of is a bolted joint that involves a gasket. So what's a gasket? It's a soft, flat component clamped between two mating surfaces to provide a seal. These are often made of paper, rubber, cork, or some synthetic material. Here's an example, a pipe flange, where there are two pipes that we need to join together using bolts, and there's this gasket right in the middle that seals between them. Here's another example, an engine head gasket. So there's a cylinder head and there's a head gasket. And here's a closer up view of a head gasket laying across a cylinder block. The head gasket, with its softer material, it is designed to fill irregularities in machined surfaces. The textbook has a nice procedural workflow for estimating stiffnesses, and I'd recommend that you have a look at this. It may be helpful for you in working through bolted joint analysis. When we're using gaskets in bolted joints, these are very soft members. If these are made of paper or rubber, it's going to be a lot less stiff than steel or aluminum. So the gaskets are going to behave as a soft spring. And imagine if we have a really small K value, that's going to have a big impact on the overall member stiffness. One important consideration in designing a gasketed joint is to help ensure that there is even pressure across the gasket. This will help seal the joint better. If we have too few bolts, then at portions of the joint that are far away from bolts may not have enough pressure to maintain a seal. We need an appropriate number of bolts. Say for this circular flange, there's a range between 3 and 6 of this quantity that's appropriate for the number of bolts in a gasketed bolted joint. So D sub B, that's the bolt pattern diameter, N's the number of bolts, and D is the major bolt diameter. This next section focuses on bolt preload and external tensile loads. Okay, recall that P is the external tensile load. Here we're assuming there's no shear. P sub B is the portion of the external load taken by the bolt. P sub M, that's the portion of the external load taken by the member. Bolt axial tension is composed of two components. We have the portion of the external load taken by the bolt plus the preload that we discussed earlier. This bolt preload is tension in the bolt shank that's due only to tightening if there's no external load applied. The resulting load on members is equal to the portion of the external load taken by the members minus the preload. Gauging from this equation, you may be able to see that the amount of preload is important. It needs to be large enough that we don't have separation between the members. And we'll talk more about separation in a few minutes. Preload is an important specification for bolted joint design. Larger values prevent separation, but also affect bolt reusability and fatigue. We'll talk about both of those items as well. Preload is often specified to be close to the proof load, 75 to 90% of the proof load. So let's talk about how we can achieve specified preload values. One way to be very confident that we have the right preload is to measure the elongation, measure the bolt before and after tightening, and then we can calculate what the preload is if we know what the other quantities are in this equation. This is the most accurate, but it's often impractical. We may not always have access to both sides of the bolt so that we can take this elongation measurement. So what's a more practical way of achieving a specified preload? We can tighten a nut with a torque wrench. So what's a torque wrench? It's a wrench that we can use to apply a specified amount of torque to a nut. And here's one type of torque wrench. It's a fairly easy to understand type of wrench. It's a beam style torque wrench. Essentially, the main structural part of the wrench is designed to bend some. And just thinking back to cantilever beam deflection formulas, this beam is going to deflect an amount that's proportional to the torque on the end of the beam, and we can calibrate the dial indicator to be proportional to the amount of torque. Another more convenient type of torque wrench is a click-style torque wrench where you can adjust a torque specification. So there's a close-up of the handle at the bottom figure. We can turn the handle to achieve a particular torque value, and then we use this wrench to tighten the bolt or the nut, and when we get to the specified value we feel a click and then we know to stop. So if we are wanting to use a torque wrench to achieve a specified preload, how do we relate torque to preload? Well, thinking back to what we looked at with power screws and thread systems, we realized that helical thread is really just an inclined plane wrapped around a cylinder. And recognizing that, we can do a static equilibrium analysis, keeping in mind that the torque is going to be equal to this horizontal load times the radius. One way of defining this torque preload model is with a linear coefficient k. So we say that the torque applied is equal to this coefficient k times the preload times the diameter. So this torque coefficient depends on bolt geometry and friction. Let's look at this in a little bit more detail. K is the torque coefficient, and here is a fairly general formula for K. Here, D sub M is the mean thread diameter. That's the average of the major and minor diameters. Now, this mean thread diameter is different from the pitch diameter that we looked at earlier. If we look at figure 8.2, we can see that the pitch diameter using this standard thread specification is actually smaller than the mean diameter. Lambda is the lead angle for the thread. 2 times alpha is the thread angle. F sub c is the coefficient of collar friction. In this case, if we're tightening the nut, the sliding surface will be between the nut and the washer. A typical value for the friction coefficient is 0.15. When F is approximately equal to 0.15, the torque coefficient can be approximated as 0.2. Let's talk about bolt tensile stress. The axial bolt tensile stress is equal to the actual load in the bolt divided by the tensile stress area. We can get the tensile stress area from table 8.1. If we're focusing in on yield as the failure mode, the safety factor for bolt yield is equal to the proof strength divided by the axial bolt tensile stress. We can obtain the proof strength from table 8.9 or other appropriate tables. This depends on the grade of the bolt. Often bolts are loaded close to proof strength. Doing this improves cost efficiency. We can get away with smaller bolts or lower grade bolts. And having a high preload improves separation performance. Here are some specification guidelines for preload, and they depend on whether you intend to reuse a bolt or not. So if you want to reuse a bolt, it's a good idea to limit the preload to 3/4 of the proof load. But if it's a permanent bolt not meant to be reused, you can increase the preload significantly. It's important to make sure that the load applied to the bolt does not exceed the proof load when an external load is applied. Another way of describing or quantifying a design for a bolted joint is using a load factor. This is an alternative to using a safety factor. This involves the stiffness constant, just a reminder that it involves the bolt stiffness and the member stiffness. This load factor quantifies how close to the proof load the bolt load, the load the bolt is actually experiencing, is. Okay, let's talk about another failure mode, bolted joint separation. Now, we're going to look at a video from an activity that we go through in this class where students design a bolted joint and then we test it and see how it performs. And so what we're looking at are 2 flanges, 2 members. Here's an upper member and a lower member, and we're using a hydraulic ram to pull this joint apart. The arrows there point to some bolt heads. There are several bolts around in a circle. It's a little bit hard to see, but I want to at least describe it before we look at the video. So we apply an external tensile load, and we can measure the elongation and measure the force as we apply an increasing load. Okay, let's see what happens. That broke rather quickly. Okay, now watch the joint between the 2 flanges as we apply a load. We're going to look for some separation. Okay, it looks like it's starting to separate now. The gap is getting larger. We don't have rupture yet. Now we have rupture. Let's talk about how to predict and design to prevent bolted joint separation. Member separation is important to avoid. It can cause some type of functional failure, for example, leaks, or lead to other problems. One question we'd like to answer is, for a given design, what is the maximum load that we can apply, external load, without separation? Also, based on models we're going to go through for separation, what could be done to the design to increase separation load? The force between connected members is going to be equal to the portion of the external load taken by the members minus the preload. And based on the earlier formulas we went through, it can be rewritten as the quantity 1 minus C times the external load minus the preload. When F sub m, the force between the connected members, is equal to 0, this is where the joint is at the verge of separation. This is what we want to avoid. To find what this threshold value is for the load that's going to cause separation, we're going to set F sub m to 0 and then solve for the external load to find P naught, or the separation load. So here's the separation load. That's equal to the preload divided by 1 minus C. And then we can also define a safety factor against separation. Let's try to see if we can get some design insights from these formulas so that we can learn how to better design a bolted joint to resist separation. So here's the separation load. Here's the load factor. So we really have two competing things going on. We want to improve separation performance, but we also want to improve structural performance. Or in other words, we'd like to prevent failure from having the stress of the bolt reaching the proof strength. So if we look at preload in both of these equations, we can see that increasing preload protects against separation. But if we increase preload, it reduces the external load at which the bolt will reach the proof strength. So it's good for separation, but not good at protecting against yield. Let's have a look at the effect of changing C, the stiffness coefficient, on both of these performance metrics. If we increase C, or in other words, increase the relative bolt stiffness, this is going to improve the separation load, but it's going to decrease the load factor. Increasing the preload requires either a larger or stronger bolt, or preloading closer to proof load. In other words, if we're starting off with a reusable design and we increase the preload without increasing the strength or the size of the bolt, then we're going to end up with a non-reusable joint. Using larger or stronger bolts will also improve the load factor, but of course that's going to increase cost. So here we have conflicting phenomena that make for actually a really interesting non-trivial design problem. And so part of the job of the designer is to balance these competing phenomena and try to figure out what design is best for a particular application. Let's talk very briefly about bolted joint fatigue failure. The existence of preload biases any fluctuating internal loads toward tension. The preload on a bolt, that is a tensile force. If we have a positive mid-range stress, this reduces fatigue performance. We can calculate alternating and mid-range stresses in a bolt using these formulas. Here, this term on the end, this preload shifts the mid-range stress to positive values, and this, of course, accelerates crack propagation. P sub max, that's the maximum load experienced by a bolt, and P min, that's the minimum load experienced by a bolt. To calculate these, you're going to need to have a look at a fluctuating external load, and then what load does the bolt itself actually see as the external load is fluctuating? You're going to have to take into account the stiffness coefficient as well as the preload in these calculations. Once we have these stress values, we can apply standard fatigue failure criterion, and we can also calculate a safety factor with respect to fatigue. Let's have a quick overview of one possible way of going about the bolted joint design process. This is something that may be useful later on as you go through the group bolted joint design activity. This is just one possible process. There are definitely other ways of going about this. Suppose that we are given a member design and also a specification for a minimum separation load, and also a value for a maximum load that the joint must tolerate without failing, without rupturing. So use this relationship to create an initial design. You can choose the number of bolts, the thread area, the proof strength. Once you look at the relationship between these, we can see, well, what's going to help us satisfy the maximum strength requirement? And once we have that, we can calculate the member and bolt stiffness values. With those, we can specify an appropriate preload and corresponding torque value. Then we need to check the safety factors for proof load, separation, and fatigue. We only need to worry about fatigue if we have a fluctuating external load. If we have satisfied these safety factors, then great, we're done. We can deliver our design. If not, then we need to make some adjustments. And so this is where some of the design insights that we've talked about earlier come into play. It's helpful to understand the influence that certain design decisions have on different aspects of bolted joint performance. So we may need to adjust preload, but as we talked about before, increasing preload is going to require a stronger bolt. We may need to increase the grade or the size of the bolt. We may need to also look at increasing or decreasing the number of bolts in the assembly. We may need to adjust the grade and the tensile stress area or the size of the bolt. Another thing, if there is some flexibility in the members, maybe adjusting the member stiffness would have a desirable impact. Remember that changing the stiffness coefficient C has a different influence on different performance metrics. And so adjusting member stiffness or adjusting the bolt stiffness may have an impact that helps you get a feasible design. So in summary, we talked about analysis and design of bolted joints. We looked at force analysis. We covered several different failure modes. We learned how to model bolt and member stiffness. We discussed preload and torque specifications. And coming up in class, there's going to be a detailed example covered in class. And also, bolt characterization is something you'll need to learn how to do, how to take measurements from a bolt and characterize it. There's a video available for performing this. And also, upcoming is the bolted joint design and testing activity. This is a group homework assignment. This concludes the video. Thanks for your time.